The standard hydrogen electrode is the actual reaction that is used as the control, or that the half reaction that is set equal to 0. All other reactions will be paired with or against that, and thus the reduction potentials for other reactions can be determined. In our B4, we assign an arbitrary value of 0 to our copper 2 plus copper half reaction. But in the standard reduction potential, the hydrogen electrode is the one that has been assigned a value of 0. What is the standard hydrogen electrode? Well, we don't have one at school. It's a fancy test tube with a connector in which hydrogen gas can be blown down over an inert or maybe platinum or gold electrode, and so these are bubbles of hydrogen. So since excess hydrogen is pushed down over the electrode, excess hydrogen will bubble out. And hydrogen ions in the solution can gain electrons to produce hydrogen gas, while hydrogen gas could turn into, through oxidation, into hydrogen ions. Now, which one of these happens depends on what chemical this standard hydrogen electrode is paired with. But both of these values would be equal to 0. It might look something like this. Here we'd have a zinc electrode paired with our standard hydrogen electrode, and since zinc is more active, zinc will oxidize while the standard hydrogen electrode is reduced, meaning the hydrogen ions in solution will gain electrons. The voltmeter will tell us that the zinc is the anode, because when the voltmeter reads positive, the black lead will be where oxidation occurs, and the red lead will be where reduction occurs. Since this is equal to positive 76, but of course the hydrogen is 0, and we can see that the zinc is connected to the black lead, the oxidation of the zinc would be positive 0.76. Thus, the reduction potential of the zinc 2 plus would be the opposite sign. Let's look at the standard reduction potential table. You have a link to this particular table, and notice that the hydrogen reduction, or we can think of the opposite, oxidation, has been set equal to 0. This is of course occurring in solution and at 25 degrees. In this course, all of your solutions for electrochemistry will be at 25 degrees Celsius. Since our voltmeter in the lab was reading 0.8 or 0.9-ish, we can now calculate the theoretical value from the standard reduction potential table. Instead of using the copper as 0, we'll use the actual standard reduction potential table and look up copper. You want to notice that there are some options, but we need to pay attention to the fact that it's copper 2 plus in solution and turning into copper solid. Hence this reaction. And zinc, of course, turning into 2 plus, we search down the table and we'll find zinc reduction. But of course, what's happening in our lab is that the zinc is being oxidized. We always have to have an oxidation paired with a reduction. You can't have two reductions happening, or you can't have two oxidations. There must be one of each. So we find these values, and we take the reduction value, which is the copper, and we add it to the oxidation value. Again, we have the zinc reduction, but because it actually is an oxidation, we'll use positive 0.76. Add them together and get a value of 1.10. It's really important to be aware that when the reaction is flipped, the sign of the voltage is changed. If you look at a text or if you look online, you may see this equation. Instead of the one that I would prefer to use, E reduction added to the E oxidation is equal to the E combination or the E cell, you may see E reduction minus E reduction. That seems a little confusing to me. The fine print, of course, is that the E reduction that you're subtracting is for the electrode that is oxidized, and so this minus sign is essentially flipping this reduction, which is negative 0.76, flipping it and turning it into the positive 76 for the oxidation and adding those together. The punchline of all of this is that a voltaic cell, a galvanic cell, or a battery will be thermodynamically favorable. It will actually happen if and when the E cell is a positive value. Again, we had positive 0.8, 0.9. The actual value should, in theory, be 1.1 volts. A few important features and vocabulary that we might want to pay attention to. I've been calling these containers half cells or compartments containing the particular appropriate reduction or oxidation chemicals. The piece of metal that is stuck in the solution is known as the electrode, and AP is going to give very particular names to those electrodes, and where reduction occurs we will call it the cathode, and where oxidation occurs we'll call it the anode. So we've got some acronyms to remember that. REDCat, reduction at the cathode, or ANOX, oxidation at the anode. Another way to notice is the two that go together both begin with vowels, and the other two that go together both begin with consonants.